Welcome to my overview of Elasticsearch. I will be presenting this material by walking through the complementary Git book, which is hosted publicly here at this URL. Speaking in terms of a relational database, of which Elasticsearch is not, it's a document database, an Elasticsearch index, at least before version 6, could sort of be thought of as the database. This is an old slide that shows this. You could store many different types of data in it, similar to the way you can have many different tables, where each contains a different type of data, and a relational database. That's all changed starting with version 6. Now an index is more like a table. You can only store one type of document per index. We're only going to work with one index, articles, for this simple demo. Elasticsearch is easy to get started with, but you can quickly find yourself in the weeds because it has tons and tons of features. We're just going to keep things simple. Let's start by verifying we're starting from a clean slate. Issue a git command against the articles index. The response is a 404. Now let's create the articles index. We'll map a single article type into it. Article has two text fields. These are fully searchable. There are many different types of fields, but we're keeping things simple. The response looks good, and we can now verify that our index was created. We'll issue a head command this time. We can see the index is there. The response also includes information about the cluster, but like a lot of things we'll see along the way, that's outside the scope of our immediate discussion. We can go a little further and even verify that the articles type exists by using the mapping API. The response looks good. Now let's work with some data. We're going to get into the document APIs now. We'll start off by posting a new document to the articles index. It'll be of the type article. We'll assign it an ID of 1 so that we can track it. Otherwise, the system will assign it some sort of GUID thing that's impossible to track well. This particular data structure kind of simulates what you would want to do if you wanted to search on terms and with your results be able to click results and have it navigate to the path on your website, something like that. Well, I'll show you an example of that later. Anyway, so we'll go ahead and post this new document, and we see a response and it looks pretty good. Let's fetch it to make sure everything's intact, and we're going to specify just the source. This is going to exclude the metadata. So what's coming back is the source that we added and none of the metadata around it. Next thing, we'll use a script to update this new document. So we're going to do a post, and these little escapes here are for the single quotes to make it play nicely with curl. So we're updating document 1, and we're just modifying the page text, and the response looks like everything worked okay. We'll fetch that thing, and we'll note that the page text has been changed, and also the version number is 2, not 1, because of the update now. Now we'll try a different approach to updating. This will be what they call the partial document approach, and this will just reset the content back to that of the original document. So again, we're posting against Article 1, and we're just updating the page text, not the whole document. And we see the response looks fine. We'll fetch it again just for good measure, and we'll note that the version number has gone up, and the page text has been modified. Now let's insert a new document into our index using an upsert approach. This is going to be document ID 2, and with the upsert, what happens is the upsert element gets executed if the document doesn't already exist, and the script gets executed if it already exists. So we'll see the first time we post it, we get a response. We got a version ID of 1. Let's go ahead and fetch that just to make sure everything looks okay. And we can see that the page path and page text went in there. We've got a version of 1. So indeed, the upsert element was what was applied. Now we'll resubmit the upsert request, but I'm going to modify it to make it even more obvious that only the script is used on the update. So you can see the page path and page text are kind of nonsense. We apply it again. The response looks good. We'll fetch the document, and we see the response is version 2, and we can see that the page path has been amended, like as specified in the script. The page text is still the same. So indeed, the script was executed on update. Now let's take a look at all of our data using a multi-git approach. You just specify the IDs in an array, response comes back, all the page path and text, everything looks good, and the metadata surrounding it, we've got the version numbers, everything looks really good. Next thing, we're going to get into the search APIs. Okay, this is where things start to get interesting. We'll start with a very simple search using the REST request URI, and we're just going to get all the documents that already exist in our index, and we can see that we've got 2, and we can see them just listed in order. The score is 1 for each, and that's because we're not really searching on anything. It's just a search all. The equivalent of that using a request body approach is right here. So you can see our query is a match all. and the results are exactly the same. The score is 1. We weren't really searching on anything. We weren't restricting our search at all. We were just getting everything back. So it didn't make sense for the score to be anything different than a 1.0 because everything is a perfect match when you're fetching everything. Anyway, let's look at our data without including any source at all, and we'll do another match all. This is just another interesting way of looking at things, so we can just get back our metadata. So again, we got ID 1 and 2. They're both perfect score of 1 because we're not restricting our results in any way. Now let's look at our data including only specified source fields, and you might want to do this if you have a lot of fields in your source, and we'll filter the metadata to only include the hits object. So that's out here, the filter path is out here on the URL. In the body, we're restricting the source to just the page path, and we can see the response is accordingly. Again, the scores are still 1.0 because we're not doing any restricting really on what we're getting back other than the shape of the data. The next thing we'll do is a text search. This is just a simple text search, and note that the matches are ORed. We're also going to have different relevance scores because now we're restricting what we're getting back. I'm also providing some custom highlighting so that you can see the start of a match is going to be marked by a match open element and the end of a match by the close. The fields are the page text, that's what we're looking at, and the fragment size is going to be 40. So let's go ahead and issue that, and we can see our response comes back. And we see ID 2 comes back first, ID 1 comes back second, and that's because the score was weighted more heavily for ID 2. It had a more dense match. And you can see those custom matches there, like surrounding Harvard. And you can see that the highlighted matches are 40 characters long. So that's adjustable, but I figured that would be readable for this demo. Let's go ahead and do a text search here, and we'll override the default sort, which is by relevance score, which is what we just saw. The scores are now not applicable, and therefore they're not calculated. So we'll issue this query, and we get our response back, and we can see the ID is now 1 comes through first, and 2 second, and the scores are null. They're not even calculated. Let's go to a text search. This is getting a little more interesting, and we will require a minimum number of matches for a result. So we require that the results only include documents that match all of these terms. Well, at least 4 of them. So that's down here. I misspoke. Anyway, okay, we're still doing our custom highlighting just to make it easy to follow. And the response here, we only get 1 back because only ID number 2 had enough of those to constitute a hit. Let's look at the text search again, a Boolean with multiple fields this time. So we're looking at something with a page text that includes Jones in it and a page path that does not include Jones. So the only response that comes back is ID number 1 because the other one had about Jones in the path. All right, let's go to a phrase match. There are no matches, though one might have expected document 1 to match. So we're looking for innovation-driven group of specialists. These aren't ORed. This has to match exactly that phrase. And our response is we get no hits. So we'll look into analysis next, and we'll see why that happened. Analysis and analyzers, it's a big topic. An analyzer consists of 0 or more character filters, a tokenizer, and 0 or more token filters. The documentation, the official Elastic documentation covers this pretty well, so I'm not going to get into it here, but I'll just show you how things work. We're going to analyze the text of document 1 to see how Elasticsearch sees that text by default. So we're going to be posting against the Analyze API, and there's the text we include with all the markup and everything, just as we had it before. And as we see in the response, it's broken apart that text string, and it's included things like the HTML tag names. You can see the superscript there. You can see strong in there. So that explains why that phrase search didn't work before, because in that phrase that we ended up the last section with, strong is in the middle of that phrase in terms of Elasticsearch, even though you wouldn't think it would be normally. Let's look at the text of document 1, that same document, without specifying the index. And this is default analysis behavior, so really whether or not you specified the index, it doesn't matter. The results are going to be the same as in the previous example. Now let's analyze the same text with the custom equivalent of a default analyzer. So this is how you build an analyzer. And this is just using the standard tokenizer, standard filter, and we're lowercasing everything. That's why all my matches have worked regardless of whether the case is matched. And then we feed in the text. Exact same results. Now we're going to conduct a search matching the entire phrase. This time we'll include that HTML tag name of strong. like we didn't before at the end of the last section, we will include it here, and we will see that this time we do get a match. So what we were suspecting by looking at the analyzer results earlier, that strong is being picked up as part of that phrase. Now we're going to build a custom analyzer. To do this, you first have to close the index. So we're going to issue a close command against the index. It was acknowledged, and we're going to create a custom analyzer to strip out, or rather ignore, the HTML tags. I say ignore because those tags are still in there, as you'll see in the results. They're still in that source. And we're going to make that analyzer the default analyzer for that index. So we're stripping out the HTML there, and we're still lowercasing everything. Our response, it's acknowledged. We reopen the thing, the index, acknowledge, and we have to check the health of the cluster. I think is a good idea. I've had certain times where it's come back and the cluster is red, or it's in a state where it's not ready to operate yet. Usually when it's in that situation, I just wait a little bit and maybe close and reopen it. In this case, we're green, so we're good to go. So now we analyze the text of document number 1 without specifying the index, as we've done before. This is still the default analysis behavior. It's unchanged by our index update because we haven't specified the index yet. But now this time we're going to specify the index, and note the removal of the HTML tags in the analysis. So even though we're still showing it the same text, we don't see strong in there like we did before. Okay, so we'll issue a command to do a match, which includes strong in it. And this is just, one of those OR matches. And notice that the strong word is no longer highlighted because this new analyzer is being used to query. So in our response, we see other things that are highlighted, like Harvard and so on, but our strongs are no longer highlighted. This illustrates the fact that indexing with one analyzer and querying with another is going to be problematic. You're going to get inconsistent results. This next thing really shows it. Now we're just showing, we're searching on strong, and in our response, we do get 2 hits back, but nothing is highlighted. So when we indexed the document, that stuff is processed so that strong is in there and it's able to be detected as a match. But when you go and try to fetch it out, it can't highlight it correctly because the positions are off. So what we'll do is update all the documents in the index by using the update by query. And this is going to correct all the analysis inconsistencies. It's basically reposting all the documents all in one fell swoop. The response, everything looks good, everything was updated, and we can do a search. We'll search on that phrase. It's the phrase match that we closed out the last section with, and this time it works as expected. So as we can see, we get our match, and strong is not highlighted. This time we can see that strong has been symmetrically excluded from the analysis. So we specifically search for strong, and this time we get no hits back. So it's completely under the radar now. It's been eliminated from what the analyzer sees. Now we'll get into something even a little more advanced. Okay, time to look at character mapping and synonyms. So we're going to tweak the analyzer a little bit more. We'll first start off with a baseline search before we do any more customization. This is one of those OR type of searches where if and, or countries, or weasels, or overpriced, if any of those things were hit, if they were matched on, that would count as a hit. We look below and we can see like the and symbol in document number 1 wasn't picked up. Countries was matched, weasels wasn't, overpriced was not matched. So let's go ahead and modify our custom analyzer because we do want to match on some of those just to be creative, show what we can do with this thing. We'll first have to close our index when we want to modify the analyzer, and we see the response looks fine. Now we're going to add custom character mapping. So we're going to map from the and symbol to the and word. We're also going to add a synonym token filter. So attorneys will look to Elasticsearch like weasels and Harvard like overpriced. So anywhere where we're searching for weasels, if attorneys is in the text, we should be able to get a match on that, and similarly for overpriced. So once we apply that, we can see that the change was acknowledged. Let's reopen the index and make sure everything's still green, and it is. So let's revisit that initial search where we had the and countries weasels overpriced, and we'll see the effect of it. This time we get a response where we can see the and symbol in document 1 is matched. We get Harvard matched because of overpriced. We got attorneys matched because of weasels, and countries that is still matched. So you can kind of bend reality a little bit with some of these mappers. It's very interesting. The only thing really left to do at this point is to clean up our mess. So we'll post a delete command against our articles index. That's acknowledged. And we will issue a head command again to check for the existence of that index, and it is gone. So we've cleaned everything up. As far as the article data structure, I mentioned that I'd show you something about that later. A website that we designed, we use that for a full text search of the website. Basically, every screen, every page, we just took the text and concatenated it, and that was the page text, and then the path was the path for that page, so that it could easily be served up in a search result, as we'll see. We'll search on, I don't know, kills, continues, same, and designed, and we'll show you the results here. And then here on the results, we can see highlighted kills, continues, same, and designed. These are all the little match strings, and they've been kind of concatenated together with a little bit of formatting, you know, the little ellipsis separating them. That's just a stylistic thing, but these are all the matches. And then the Y switch is just a nice label over the page path. So if I click that, I navigate back to the screen that had that text on it. It's important to note that the formatting on the search screen, the search results, we had to strip all the HTML tags out, and I'll show you that in a second. Going back to our demo, this shows the formatted contents of the first two documents here at the top of the page. And then below that, we see what the search results looked like if we hadn't stripped the HTML tags out. You can see broken tags would sometimes have an unmatched strong or something where it would start the element and never finish it. And the results were unpredictable and would lead to problems with formatting. So we used a little bit of custom code and a JavaScript library to remove out the tags before we indexed the text into our Elasticsearch index. And then when we were able to pull it out, the results looked better. They were formatted correctly, as you saw on the live site, and then also right here with our little contrived demo. So that concludes everything. I hope you enjoyed it very much, and we'll talk to you later. Thanks. Bye.